All right, so today we will look at more NumPy stuff, okay? So here, let me clear all outputs. Okay, so once again, we will begin by importing NumPy as NP, and that way we can kind of refer to all of the NumPy functions, a little bit faster by doing np dot whatever. All right, so the first thing I want to show is kind of joining, concatenating arrays. So here I've created two arrays. These are both one-dimensional arrays. So basically, a length 4 array going from 0, 1, 2, 3, and then another length 4 array going from 100, 101, 102, 103. Okay, you can do concatenate. And for concatenate, you provide basically either a list or a tuple of the arrays that you want to join together. And so this does exactly kind of like, so this is kind of like using the plus operator for lists, right? When you have a list and you have another list and you do plus, it joins them together. So here we're going to do np.concatenate, and it kind of attaches this array to the other array. Concatenate comes with an argument which specifies along which axis do you want to concatenate. So here we want to say we want to concatenate along the zero axis, right? So axes are zero indexed. Everything in Python is zero indexed. So the first axis here is basically the length of our array, and so we can say concatenate along the zero axis, and it does this. Okay. Now we might want to say, okay, well, what if I want to, I have a length 4 array and a length 4 array, and what if I want to create a 2x4 array, right? I want to have 2 rows and 4 columns here. So you can say, like, let's try to concatenate along axis 1. Okay. But if you do that, it throws an error, okay? It throws an error. And the reason why you can't concatenate along axis 1 is that there is no axis 1, right? If you look at the shape of x, there's only one dimension, okay? So it's kind of like, if you have a line and another line, lines are one-dimensional shapes, right? You can join two lines together and you get a longer line. But can you stack a line on top of another line? You can't, right? You can take a rectangle and join it with another rectangle, and you get a wider thing. But you can't take a line and then stack it on top of another line. And that's basically what we're trying to do here. We have this one-dimensional array, and we're trying to attach it in a second dimension. So we can't do that. If you wanted to do something like that, you could do vstack, and vstack will kind of induce a second dimension. So this is vertical stacking. And so if you do that, you will get a 2x4. So that's vstack. You take the arrays and you stack them vertically. What we can do is I can reshape x into a 1x4 array. Okay. And so if I reshape x into a 1x4 and reshape y into a 1x4, okay, so here I can say concatenate along axis 0. And what we get here is that when in the reshaped 1x4, axis 0 is the rows. So if I say concatenate along axis 0, we are going to be adding this one row to this one row, and we end up getting 2 rows and 4 columns. Okay, because axis 0 in a 1x4, axis 0 is the row. So when we say concatenate along axis 0, we're adding rows. If I say axis 1, okay, axis 1 in a 1x4 is the number of columns. So if I say concatenate along axis 1 after I've reshaped x and y into 1x4 arrays, then we will get 1 row but 8 columns now. So I kind of would just want to pause for a moment here and just make sure that we understand why when I concatenate x and y along axis 0, I get a length 8. And over here, when I concatenate the reshaped x and y along axis 0, I get a 2 by 4. And over here, when I concatenate along axis 1, I get a 1 by 8. Because we're concatenating along these axes. And so when you reshape them into 1 by 4s, axis 0 is the row. And concatenating along the row means you're basically adding rows. Yeah, question? Or no? Okay. Yes?
So axis 0 means by rows, and axis 1 means by columns?
If you have a two-dimensional structure. So when you... so you have to kind of get used to the order in which Python, the order of axes here. So for a two-dimensional structure, the order of axes is rows first. Rows is index 0. Index 1 is columns. Okay, but if you have a three-dimensional structure, your index 0 is like the number of sheets, and then I think it becomes, wait. Now, I'm confusing myself for a second. I think it's like layers, then rows and columns, or is it rows, columns, layers? Oh gosh, okay, I'm forgetting the order of axes in a three-dimensional structure. My brain's just pausing, but you have to kind of just remember the order in which Python has the order of the axes there. So I'm pretty sure I have an example just in a couple of moments here. Okay, so here I'm going to create a 2x3 array, xm and ym, xm being basically a matrix 2x3, ym being a matrix 2x3. Okay, and so here I've got 0, 1, 2, 3, 4, 5, and then 100, 101, 102, 103, 104, 105. Okay, so the shape of xm is 2x3, the shape of ym is 2x3. Right, so when you ask, what is the shape of this thing, it's going to say 2x3. So axis 0 corresponds to the 2, axis 1 is going to correspond to the 3. Right, so you think of like what is the index position of your shape? That's how it's going to go. So the default is to concatenate along axis 0. So when I concatenate along axis 0 here, what is the new shape going to be? Yeah.
2x6.
Is it going to be 2x6 or 4x3? Yeah. It'll be 4x3 because axis 0 is the 2. Okay, axis 0 is the 2. So when we concatenate along the 0, we're going to do the 2 plus 2, and we're going to preserve the second. So we're going to get a 4x3 here. Okay. We can specify axis 0 directly, and we'll get exactly that, 4x3. And when I do along axis 1, again, the shape of x is 2x3, and now we're going to take the 3's and we're going to add them to each other. So we will end up getting it here. We're going to get a 2x6. Right? So it takes a little bit of getting used to. Just you practice and you think about like, always just kind of keep in mind what is the shape of the matrix or shape of the array, and how does that correspond to concatenating along these axes. Okay, you can also just do VStack and HStack. These work very well for two-dimensional things. So two-dimensional things, you can always do VStack and HStack. But in higher dimensional things, it's here. Actually, I don't have one here, but let me go ahead and I will create. Bless you. Let me create. Okay, so let's go like 2 by 3 by 4. 2 times 3 times 4. So actually, I need 24 values. Okay, so I think I get 2 sheets, 3 rows, 4 columns, I think is what this will produce. But let me just check. Yeah, okay. So the order is 2 sheets, 3 rows, 4 columns. So if you create a 3-dimensional array, you get 2 sheets, 3 rows, 4 columns. So here, if I say np.concatenate xm and ym, and then we're going to do axis equals 0, okay? The result we will concatenate axis 0, so I'm going to end up with 4 sheets, okay? 4 sheets. If I concatenate along axis 1, we're going to join the axis 1 is the number of rows, so I'm going to have 2 sheets, 6 rows, 4 columns if I do axis 1. So 2 sheets, 6 rows, 4 columns. And then if I do along axis 2, okay, we're going to concatenate along axis 2, which is the 4. We're going to add those the 4 and the 4 together, and so we will get 2 sheets, 3 rows, but now 8 columns. And so we will get that. Okay, yeah.
So do the other dimensions have to match? Since
they have, the ones that you are not concatenating. So I could, I could have 2, 3, 2 here, and I could, so what is it? 2 times 3 is 6 times 2 is 12. Okay, so I'm going to have 112, okay? So xm is that, and then ym is this. And so this I can concatenate along axis 2. And then, and so I will have 2 sheets, 3 rows, and 6 columns. So that will work. But if I try to concatenate, say, along axis 0, this will fail because it's going to complain that, because here I'm trying to add, I've got, one thing that's 2 by 3 by 4, and I got another thing that's 2 by 3 by 2, and this 3 by 4 I can't add to the 3 by 2. So if I try to do this, it says it can't do that, right? So it's kind of like you have this. So here's my 2 by 3 by 4, right? And if I have another one that's identical, I can join them this way. So if I have another thing that's I need to do 3. This is harder to do. Okay, so I have a 2 by 3 by 4, a 2 by 3 by 4. 3 rows, 4 columns, 2 sheets here. And so I can concatenate along axis 0, and then I will get 4, 4 by 3 by 4. I can join them this way, and I will get a 2 by 3 by 8. That's along axis 2. Or I can also, what's the other way? I can put this one in front of the other one, and I will get like two layers, 6 rows, 4 columns that way, right? But then if I have something that's a little bit smaller, a 2 by okay, so this one I can only kind of join this way. I can't put this on top or put this one in front of the other. I can only join it along one of those axes. So so not everything has to be identical, but the ones that you are not, the axis that you are not concatenating along has to be, the axes that you are not concatenating along have to match, otherwise, the shapes don't fit, right? And same thing in a higher dimensional setting, it's just harder to visualize those things. Okay, let me go ahead and give you your first view quiz answer. View quiz answer A. Question 1 is A. Sorry, view quiz answer is A. Question 1. Okay, math operators. These I think work exactly as we would expect. So here, if I say +5, that 5 gets it's called upcast. It's kind of like recycling. Okay, and so we're going to just add 5 to every element. Here I can do x plus y, and this will do element-wise addition, okay? So unlike the list, the list, if you do list x plus list y, that concatenates them with the list, okay? But in NumPy, the plus operator is going to do addition, mathematical addition. So, and it's going to do element-wise. So 100, 0 plus 100, 1 plus 101, 2 plus 102, and 3 plus 106. Okay, same thing with the star operator. Star is going to be element-wise multiplication. You can do that. There is the dot product, okay, which is basically element 1 times element 1 plus element 2 times element 2 plus element 3, so on and so forth. So that's going to be the same as x times y sum. You can do sum of x times y, or you can just do np dot, the dot product of x and y. All right. The at sign is matrix multiplication. Okay. And in this case, if you just have these one-dimensional things, it will automatically. So again, matrix. Technically, you would have a 1 by 4 and a 4 by 1, and you would matrix multiply them. But here with Python, if you just give it one-dimensional things, it's going to just automatically do it, and basically you get a dot product. So all three of these things produce the same value of basically the first elements get multiplied, added to the next elements, and so on and so forth. All right. Okay. So you have to, I guess, be able to recognize this operator, right? So anytime, we just don't. Every language has a slightly different symbol for matrix multiplication. You just have to kind of know. Just because we don't have a symbol for matrix multiply on the keyboard, so we just kind of make things up. So R, you have %*%, which is probably like the worst symbol to use for matrix multiply, but we're accustomed to it in R. But yeah, it's but here it's the at operator, which I think is fine. Okay, here is oh shoot, I broke what my y was. Okay, let me redefine. Let me do xm xy. Okay, let me just rerun all this stuff over here. Okay, xm xy looks like this. All right. So again, plus 5, we're going to add 5 to everything. Xm and ym, that works because the dimensions match, and so we can do that. Okay. Again, all of these things, just like anything else, these operators don't modify them directly. You can do element-wise multiplication. So there's not. This concept doesn't exist in, say, linear algebra. So even though we're working with matrices, and this is a very common operation that we do on computers, is there, I don't know, is there a name for this? Element-wise multiplication in linear algebra? Not really, right? So you have a 2 by 3 and a 2 by 3 matrix and a 2 by 3 matrix, and we just want to multiply the first element and the second element, the third element, and so on and so forth. That's the star operator, and it makes sense in a computer, but when you do something like this, it's no longer linear algebra, right? Linear algebra, you're always multiplying matrices, and the number of rows over here has to match the number of columns over here, and things like that, and it's whatever, like this, okay? Sometimes you want to chain operations, okay? And so, or not chain operations, but you can also do np.multiply. np.multiply will use kind of this thing, and I think I can do xm.multiply ym like this. No, it doesn't work. Okay, never mind. I thought there was an operator, but I guess not. Okay, so we have that. Yes, question.
Is there anything special about np.multiply? Like any other arguments that might make it more useful?
You know what? Let's look up the help. Okay, NumPy multiply. All right, so x1 and x2 are arrays. What are our options? Parameters, the out nd array. Okay, a location in which to store the results. as broadcast at locations where the condition is true. I guess you can put in some kind of condition as far as where these things would go, and then a bunch of keyword arguments. No, we don't see too much. The star is an operator for an NP array. It seems it doesn't look like there's anything that much more special, I guess, if you wanted to use any of these arguments. Where did I go? Okay. Dot, you'd have to kind of transpose, so you can do, or like you can do the 2 by 3 transpose. YM transpose will become a 3 by 2, and so you'll result in getting a 2 by 2. You can do dot XM YM, and there's also the dot operator as a method of the ND array. And we have that. Okay. More basic math here. So here I'm going to just kind of print out. I've got 0, 1, 2, 3. Add a constant, subtract a constant, multiply by a constant, divide by a constant. So everything just kind of gets applied across all of the values. You can make everything a negative. You can do powers. Okay, 0, 1, 2, 3 squared. You can do modular division to get kind of the remainders. So these are, remainder 0, remainder 1, and then absolute values. Okay, so this is all very basic. I think no surprises here as far as basic math. All right, we also have trig functions. Okay, there is the math module in Python, and you can import math to get trig functions, and we showed some examples of that. NumPy also has a lot of these kind of math functions, and a lot of these NumPy functions have been optimized, and I would say that in general your NumPy functions are going to be faster than base Python, because NumPy is all designed, well, I guess the catch is assuming you're working with NumPy arrays, okay? Because in NumPy arrays, everything in the array is of the same data type. So all of the calculations have been optimized because it knows that everything is of the same data type, and so it doesn't have an overhead of having to keep track of like what the different data types are. So anyway, here I'm going to just create linear space values, 5 linear space values going from 0 to pi. So this is 0, and then this is pi divided by 4. This is pi divided by 2, 3/4 pi, and 1 pi, right? And so we can say, okay, what is the sign on this array theta? So, we get 0, and then we get, what is this, root 2 over 2, I think, 0.707, and then 1, and then root 2 over 2, and then 0, all right? So, I don't know if you guys talked about floating point math, but in floating point math, it's not real numbers, so you don't get exactly 0. The computer is accurate to around 16 decimal places. So anytime you see an e to the negative 16, even like an e to the negative 15, that basically means 0. All right. It's just the computer, for whatever reason, wasn't able to distinguish between 0 and this thing. It's kind of like on the calculator when you do 10 divided by 3 on like an old calculator. If you do 10 divided by 3, you get 0.33333, and then if you 3.33333, and then if you take that and you multiply by 3, you don't get back 10, you get 9.99999, right? And so what is 10 minus 10 divided by 3 times 3 would be like 0.000001, and that's the equivalent of 0. It's just a side effect of the computer's inability to actually have real numbers. Just we have approximations to real numbers. Okay, cosine, you get 1 root 2 over 2. Here we have 10 to the negative 17, so that's basically 0, and then negative root 2 over 2, and then negative 1 for cosine. and then tangent. We get, well, this is not quite infinity, but approaching that, okay? So, you know, so we have, this is this going from 0 to 2 pi, so this would be sine, and so we have, you know, going from this, cosine, you get this, and then tangent, you get something. Okay. Did I do that right? Okay, so I guess if you were just a little bit on the other side, you'd get negative, you know, infinity here. Okay. Same thing. So we have log and log functions. Okay. If you want common log, you do log np.log 10. Okay. So you get 0, 1, 2 for that, or 0, 2.3, and so on and so forth. Exponential e function is this. exp2 is 2 to the y. All right, so you know, plugging in 0, 1, 2 into that, you get 1, 2, 4. And then if you just have some general power, 3 to the y, whatever you want, you can do that as well. So here, 139. We have functions that will aggregate things. So here I'm going to just create integers 0 through 99. And you can do sum. You can use the base function sum, and it will add up all of these things. You can do np.sum, which will also add up these things. And so these two things look like they do the same thing. The NumPy version of the function is much faster. There's a little function called timeit, %timeit, and this will run the code like, I guess it did 7 runs, 100 loops each or something, and it times each of these things. And so you can see, you know, how long did it take to sum this big array, and it said each of those operations took 2.46 milliseconds, whereas if you did NumPy, each of those operations took 24.6 microseconds. Wait, milliseconds, ms? Yeah, this is microseconds. So this is on the order of 100 times faster, okay? 100 times faster. And so the NumPy version of the sum, again, designed to just go quickly, and so that we would do that. Okay, you can also look for the min and the max of a thing, and again, there's also the NumPy version of the min and max. And so after, you know, here we generated 10,000 values, and so just kind of our random values, you know, we got 0.0003 and 0.9997, and again, if you time this, the NumPy version is much faster. I'm going to just go ahead and skip that. All right, with matrices, okay, you can run sum and whatnot. Okay, so here I've got a 3x4 matrix. I just took the integers 0 through 11, or not, 0 through 11, and then I shuffled them. Okay, so I used random.shuffle, and then I arranged them into a 3x4 array. Okay, so sum will just take all of these things. Now, the default sum function, the base sum function, sums the columns. So you get 2 plus 1 plus 11 and 3 plus 6 plus 9, which is a little, like, to me, a little bit odd. Okay, numpy.sum does just gives you the sum of the entire matrix, which I think, to me, makes a little bit more sense. So when you add up 0 through 11, you get 66. Okay, so here's our matrix again. You can also sum across the axis. So just a reminder, you can ask, what is m.shape, right? And it's 3x4. Okay. So here we're gonna sum across the axis 0. So sum across axis 0, we're going to get length 4, right? So we're basically, when you do sum on the axis and you specify the axis, you are collapsing the axis that you are specifying. So we're saying sum across axis 0. So we're going to say sum across the 3 rows. All right. So if I do axis equals 1, okay, so axis 1 is I have 4 columns, we're going to sum across the 4 columns, and so the result will be the 3 values here. Okay, we are collapsing against the column, the index 1. Right? So if you think about the shape and you think about what axis you are specifying, I think that will help you keep track of what it means to specify the axis for the sums here. Okay, these functions like min and max and whatever, you can also specify an axis. So here, if I do np.min_m across axis 0, it's going to find the minimum across this axis. So what is our first value going to be? np.min. It's going to be the minimum of the first column, so we'll get a 1. And then the next will be a 3, minimum in our second column. So we're going to get 1, 3, 0, 5. Okay? You can ask, what's the standard deviation? Standard deviation of all 12 values is going to be 3.45. You can ask, what's the standard deviation if you did axis 0? And you'll get 4 values. You can ask for something like the mean. You can do mean axis 1, and it will give you 3 means and basically the row mean. It'll say, what is the mean of 2, 3, 4, 10? So what is that? That's, I can't add up, 7, 9, 10, 19 divided by 4 is 4.75. Okay, the mean of 1, 6, 0, and 7 is 14 divided by 4, 3.5, so on and so forth. Okay, so you get 3 values, basically your row means when you do axis equals 1. So specifying the axis collapses that one axis. Okay, so here, same kind of idea here. Here I have the shape is 2, 3, 4. Okay, 2, 3, 4. So if I do sum A, axis equals 0, what am I going to get? So what axis are we collapsing? We're going to collapse axis 0, so we're going to collapse the 2. So we're basically going to add a 1 and a 1. So we're going to get, the result will be 3 by 4, and every value is going to be 2. Okay, if I sum across axis 1, the result, I'm collapsing the axis 1, which is the 3, right? The shape is 2, 3, 4. So we're going to collapse axis 1, we're going to collapse the 3, and we're going to get a 2 by 4 of 3s. Okay, 3s arranged in a 2 by 4. And then if I collapse axis 2, we're going to sum across the 4 columns, and the resulting shape will be 2 by 3, and we have, the value is going to be 4 across all of these things. Okay, so the resulting shape will be 2 by 3. Okay, so that's what we have there. Okay, sometimes we have nan values. Nan is how we represent something that's not a number, and in Python it's also used to represent missing values. Okay, nan is a floating point value. Okay, so there's no in Python there's no way to express something is integer and missing. That's just one of the, I guess, unfortunate things. It's usually not a huge deal, but if you want to represent something as missing, it kind of has to be a float. There's no way to have a missing integer. Whereas, language like R, you have a missing value for each data type, and here nan is going to be for missing floats. So that it just looks like this. Okay. We also have infinity. Okay, the float representation of infinity is this. Okay, and if you try to do calculations with infinity, like if you do infinity divided by infinity or infinity minus infinity, those result in nans, okay? Here, if I do, what is the sum of nan plus 2? It's going to say that's nan, okay? If you have a missing value and you try to add 2 to it, it's going to be a missing value, right? Like I say, hey, there's a unspecified number of marbles in this pouch, and I also have 2 marbles out here. How many marbles do I have in total? Okay, and the answer is, I don't know, right? And that's basically what we get here. So if you want to ignore missing values, you can do nan sum. So you have like the nan safe version of a lot of these functions, and that will just ignore anytime it has missing, and it's going to say, okay, I'm going to just add the 2, and so there is 2. And so basically all of these functions that calculate things like basically take a bunch of things and collapse them into a single value, like sum, mean, standard deviation, product, variance, min, max, whatever. If you want to ignore any kind of missing value, there's basically you just do np.nan, whatever it is, whatever the other thing is, okay? And that's going to be kind of the nan version, nan safe version of the thing. Ooh, all right, I got to speed things up. Okay, second view quiz answer is A as well. Question 2 is A. All right. Okay, broadcasting. Broadcasting is similar to this idea of recycling in R, but broadcasting only works when the dimensions are compatible. So here I've got array A and array B, 1, 2, 3, 4, 5, 6, and I can add them, and we will add them element-wise, okay? If I have an array 7, 8, okay, with only 2 elements, and I try to add, so if I have a length 3 array and a length 2 array, and I try to add these 2 together, we get an error, okay? It says these are incompatible shapes. One is length 3, one is length 2. I can't, it says I can't broadcast this, right? These shapes are no good, okay? Okay, but here I'm gonna have A, which is an array of length 3, and E is a 2-dimensional array, 3 by 3, right? So here I'm going to ask to add E and add A to E. And so what this is going to do is it's going to broadcast, all right, it's going to say, all right, I want to add A to E, and it's going to add 1, 2, 3 across that, 1, 2, 3 across the next, and 1, 2, 3 across the next, right? So it's going to, we're going to get 2, 3, 4. So we're just adding 1, 2, 3, and it says, yeah, you know what, I can repeat this operation across all of the rows, right? So it's just going to kind of take that thing and broadcast that same value across the thing. I can reshape A to be a 3 by 1 array, and if I broadcast that, and if I say E plus this reshaped version of A, then it will add 1, 2, 3 to this column, 1, 2, 3 to the next column, 1, 2, 3 to the next column, and it does that. Okay, so so we have that. Is that okay? Here I'm going to take A and B, so A and B, so I got 1, 2, 3, 4, 5, 6, and I'm going to stack them vertically. Okay, so this is what I have. Here I have, so A looks like this, D looks like this. Okay, so if I do D plus A, it'll get broadcast across rows. Here C is my length 2 array, right? And again, D is 2 by 3. So here, if I do D plus C, it's going to complain. It's going to complain and say this shape is 2 by 3, and this shape is 2 comma, and it doesn't want to. It's not going to automatically like rotate the 7 and 8 into a column here. So you have to reshape it. And it will do this, okay? So when I did D plus A, it was able to do this. It didn't complain. Even though A was 1-dimensional, it just said, okay, I can just do this across the rows, and it didn't complain. But if you try to do it with this, it says, I don't like that, okay? So you have to reshape C into a 2 by 1, and then it will do, here's D, 1, 2, 3, 4, 5, 6, and it's gonna add 7, 8. So, 1 plus 7 is 8, and then 8 plus 4 is 12. Okay, so we get 8, 9, 10 across the top and 12, 13, 14 across the bottom. So now we're adding 7, 8, 7, 8, 7, 8 across there. So that's okay. So now we have a 2 by 1, and it does that. Okay, here, this is where things get a little bit surprising, I guess. Okay, so with E, I'm going to reshape E to be 10 rows, 1 column. F is going to be length 11, okay? So I got 0 through 9, 10 rows, 1 column, and then here I just have basically a length 11 type of thing. But as far as broadcasting goes, NumPy treats this kind of like one row, okay? So even though it's a length 11 thing, NumPy, when it comes to broadcasting, it just kind of treats them as this one row matrix here. So here, if I do E plus F, okay, with these one-dimensional things, Python will kind of broadcast them, will broadcast both of them simultaneously, okay? So it's going to broadcast this 10 by 1 into basically a 10 by 11, and then here, even though it's only a length 11, it's going to treat it like a 1 by 11, and it's going to broadcast this into a 10 by 11 as well, and then it adds the 2. So this is maybe perhaps a little bit surprising that the end result ends up being a 10 by 11 after it has broadcast it broadcasts E into a 10 by 11, and it broadcasts F into a 10 by 11. Yeah, question?
So it's only going to broadcast if it's like a multiple of the dimensions that's multiple.
So it has to be compatible. I don't know if, I'll have to try this out. I don't think you can broadcast like a 2 by 3 into a 4 by 3. I don't think, but maybe let me try that here. Let's see. Okay. Okay, same thing with the multiply. Here's D. If I reshape D into a 1 by 6, this will work. Okay, let me see if I can do, here is D, and then let me make E. E is going to be, so I've got E, this is E. All right, let me see. If I do D plus E, or E plus D, yeah. It doesn't know how to handle this, okay? So E is 4 by 3, and D is 2 by 3. It's not going to, even though one is like a multiple of the other, like one has 4 rows and the other has 2 rows, it's not going to like just duplicate the D and add it across there. It has to be it has to be like a 1 by 3, okay? And that it can do that, okay? It can add a 1 by 3. It could add a 4 by 1. Okay, so I could do. I'm sorry. I got to reshape that into 4 by 1. Okay, so you can do that, but yeah, you can't just do a multiple. So it has to be like a single column or a single row. Okay, but you can also do like 1 column and 1 row, and they get both broadcast into these 2-dimensional things. Okay. All right, we have Boolean operators, which will return basically trues and falses. So here is this. We can do, is x less than 3, and we'll get a bunch of trues and falses. your kind of just basically your all of your comparison greater than or equal to, and then once you have an array of true false values, you can use that to subset. And I think this is all very familiar to us. This is kind of how we do subsetting in R and stuff like that. So here I can say subset to those where x is greater than or equal to 3, where that's true, and so we get that. You can also call sum on a Boolean, an array of Boolean values, and kind of like R, the falses turn into zeros and the trues become 1, and we can do that. You can call mean on it, and again, zeros and ones, and so you get the proportion that where it's true. The negation, okay, if you want the opposite of true false, you use the tilde operator, okay? The tilde operator is what we do. So this will give you the opposite, right? If you, but you have to be careful, okay? Here, if I do tilde x equals 3, okay, this just becomes false for everything. If you leave off the parentheses, here it's going to do the negation on x first, and so tilde x is -1, -2, -3, and so that's why everything's going to be false. Okay, so just be careful if you want to do the Boolean operation first to get your true false values, and then you can negate them. All right, same thing with the matrices. You can do Boolean operators on matrices, and this does all of these things. You can do sums and whatever's on that. And then we also have element-wise or bit-wise operators for Boolean things. So here I have arrays of Boolean values, trues and falses, and then if you want to do and or, okay, this is for arrays of these things. You can use the symbol and, you can use the symbol or, you can do exclusive or, and then you also have bitwise not, okay? And then the any is, are any of the values true, are any of the values false? This is, there's, for regular old, if you have one Boolean value, you can do A and B, but it doesn't work, okay? The AND operator here doesn't work when you have arrays, okay? Because this is expecting, so you can do true and false, okay? So that's fine. But if you have an array, okay, if you have an array of these things and you try to do AND, then it complains. It says you're not allowed to do something like that. Okay, so for an array values, you have to use the ampersand operator or the the OR operator here. Okay, for arrays of values. So that's something a little bit you have to kind of keep in mind. I guess you can think of the analogy in R as you have in Python you have and then in R you have the double and sign for single value ands, right? Single values. Okay, so it's kind of like that. All right, this is okay. I'm going to just have you read read the notes on your own. I think these are simple enough, but basically, if you can take like an index here, and you can subset on the index. So here's this matrix, or not matrix. Here's this array, and you can say I want element 0, I want element 1, and element index 5, and you're going to get the 37, the 12, and the 5. Okay. Same thing there, and then so if you have a matrix here, you can say I want I want to get these particular. So here I have a matrix of indices, and I'm going to subset x based on these index, and so this will pull out the 12 and the 75 and so on and so forth. Okay, and then here I can specify the rows and the columns. So I can say I want row 0, column 2, and I'll get the 2. I can get row 1, column 1, and I get the 5. Row 2, column 3, and I get 11 there. And then we have sort and argsort. Argsort arranges things so that when you when you take the, this is kind of like it'll tell you the values so that if you subset y using the argsort, it will be in sorted order. Okay, so here if y is 5, 2, 1, 4, argsort will give us 2, 1, 3, 0. Basically, the first element should be index 2, the next element should be index 1, the next element should be index 3, and then the next element will be index 0 to get it in sorted order. Okay, and then similarly, you can sort along rows or columns as well. But we'll wrap it up there. Last view quiz answer is the letter B. Letter B. So question 3 is B. Okay, we'll wrap it up here. Have a great rest of your day, and we will see you on Friday.